Welcome to Study Loop.
So once again, welcome to a new problem. This time we have a frame and it's hanging with the spring. So this is the information we're given. We have a frame. It's hanging like that uh, with the spring, and then it just happens that um, we don't know what the spring constant is, but we do know that the mass of the frame is 0.150 kilograms. That's what we're given. It's suspended, and it happens to stretch the spring a distance of x. So this string is stretched a distance of x equals to 0.04. So this is 0.04 meters, or 400. We want to call it 0.0400 meters. So that's how much the frame stretches the spring. Okay, that's what happens. And then in a second scenario, what's going to happen is that we still have the spring, but this time it stretches further. And we'll talk about that. The reason why the string is now stretching is because we have dropped something inside of it. So we have dropped a, a, a what we call a party. Okay, so we've dropped a party inside of it, and now what happens is that we have a new stretch. We have a new stretch, and we're gonna call it d equals to uh, 30 centimeters and change that to meters. So 1 meter per 100 centimeters, and that evens out to 0.3 meters. That's how much it stretches. It happens that the mass of this party is, so I'm going to call it MP, happens to be 0.200 kilograms. Okay, so that's the information that we're given. And we want to find the maximum distance. We want to find the maximum distance that it's going to stretch. Let's just call this height. We're going to call it h. Okay, we're going to call it h. That height, this height, we're going to call it h. So we want to find the maximum stretch distance when you drop this, when it goes all the way up until the base of the frame. So we want to find d, as you call it. There are a couple of things we're not given. For example, we don't know what the spring constant is. We're going to have to find that. Let's move to the next page. In the next page, we're using the law of Newton's second law, and this one says that uh, the force equals to or rather, the sum of the forces. The sum of the forces equals to mass times acceleration. But here, our force happens to be from the spring, and that's gonna equal to the mass of the putty and the acceleration due to gravity, and therefore this can help us compute the spring constant. So it's mpg uh, over x, and that gives us 0.150 kilograms. 0.15 kilograms times 9.8 meters per second squared. And then we want to divide that by the uh, the initial stretch, which is 0.04 meters, and you can see that's what's happening right here. So initially we can get the spring constant that just based on initial uh, conditions, and then remember that the the party is going to fall, and so its potential energy transforms to kinetic energy. So initial potential energy, MP G H, we have to go back and see what our H is, MPGH. So this is the initial potential energy is all transformed to kinetic energy, which is 1/2 MP V, and here V is the velocity of the party as it falls. V P squared, the masses cancel out. These two comes to this side, so we have Vp squared equals to 2gh. And so the velocity of the party as it falls becomes square root of 2gh. And we plug in the numbers, we get 2 times 9.8 meters per second squared, and then times the height, which is 0.30 meters. And then we get 2.425 meters per second. So that's its speed when it's falling. This is the speed of the party when it's falling. And then in the next page, we have to talk about the common velocity. So what happens is once it falls to the base, both of these two items are going to move with a common velocity. So both the party and the frame, and we want to find what this velocity is. We use the law of conservation of momentum, which says that the initial momentum equals to the final momentum, and so the initial momentum is the mass of the party and its velocity plus the mass of the frame and the velocity of the frame. Remember, the initial velocity of the frame is that it's not moving. Okay, it's not moving, and then we combine both of them are combined together with a common velocity, which we call Vp plus F. And we're going to solve that common velocity by moving things around using the law of conservation of momentum. We're dividing by the sum of the masses, and so the mass of the party is 0.200 kilograms times 2.425 meters per second, and then we add 0.150 kilograms times the velocity, which is 0. Remember, this one, it's not moving initially it's not moving, so the velocity of the frame, as we call it, is 0 at the beginning. This F stands for frame, and then we divide that by the sum of the masses, so 0.150 kilograms, and then times or rather not times but plus 0.200 kilograms, like that, and this gives us 1.385 meters per second. So this is the combined velocity of Vp plus F when you have the party and the frame moving down together. In the next page, we'll conserve energy. So we're gonna conserve the energy in the system, and we'll say that according to the law of conservation of energy, law of conservation of energy, the initial potential and kinetic energy is equivalent to the final potential and kinetic energy of the system. So this is we're talking about once this thing is falling inside. So the initial kinetic and potential equals to the final kinetic and potential. And so the initial kinetic of the system is 1/2 mass of the party plus mass of the frame. And then their common, here we'll talk about the common velocity squared. And that happens to be pf squared. And then plus the potential has to do with the spring itself, 1/2 kx squared. And then also the potential has to do with the two masses moving together initially. So, initially we know that there's there's going to be the initially, they're moving together. So we'll have the mass of the party plus the mass of the frame times g, which is the acceleration due to gravity, and the specific displacement, and that's going to equal the final case. Remember, it comes to a stop, so the final kinetic energy is 0, so we only have to think about the stretched spring, which is 1/2 x plus d. Now it's stretched. Initially it was x, and now there's an additional displacement, and that's going to be squared. And then, as you can see, the we can multiply everything by 1/2, but there's something else we want to recall, is that initially also the displacement is 0, so this is going to be 0, so we're left with 1/2 mp plus mf vp plus f final squared plus 1/2 kx squared equals to 1/2 x plus d squared. So that's what we're left with. We'll multiply. We'll have to multiply everything by 2. Well, actually, you know what? We have to backtrack a little bit, real quick, so we don't make any mistakes. So this displacement, it's not 0. We have to account for it. There's a displacement there. So we multiply everything by 2 to eliminate this fraction. So this side, the whole side, we multiply that by 2. And then this side we multiply by 2. So we end up with mp plus mf vp plus f squared. And then we'll put the other mp plus mf next to it, gd. And then, this is a plus, sorry. This is a plus. And then plus 1/2 kx squared. That happens to be x plus d squared, like that. So we're on track. These two are common. And so in the next page, we're going to make that common. We'll say mp. So for the most part, this is just algebra going on right here. V p plus f squared plus 2gd. So we're saying, where did this 2gd come from? We multiplied everything by 2. So there was supposed to be a 2 right there. And then on the other side, we have plus kx squared equals to k x plus d squared. Our target is this displacement, the final displacement. That's what we're looking for. Plugging in the numbers, we get 0.200 kilograms plus 0.150 kilograms. The final velocity for both of them is 1.385 meters per second squared, plus 2 acceleration due to gravity, 9.8 meters per second squared, and then times the displacement, plus, remember we got the spring constant, which happened to be, if we go back at the beginning, our spring constant, oh, we forgot about that. We plug in the numbers, is 36.75 Newton per meter, like that. And then we have to put in the 36.75 Newton per meter. Okay, we have that. And then the next thing that happens, we have to multiply that by x squared. Our x is 0.04 meters square that. On the right side of the equation, we still have the spring constant in Newton meter. This time, we still have the x, 0.04 meters, plus the displacement, like that. And then when you simplify that, you get 36.75 d squared. Now everything is in meters, minus 3.92 d, minus 0.06714 equals to 0. Notice this is a quadratic, and so we're going to use the quadratic equation. In the next page, we get to have the d, which is a displacement, equals to negative. If you go back, make sure you get the numbers right, 3.92, negative 3.92. And then we have plus minus radical, negative 3.92 squared, minus 4, 36.75. And then right here, times 0.6714. All of this is going to be divided by twice 36.75. We're using a quadratic equation, and this is the quadratic formula. And so the final happens to be, so we have to change that, so it becomes d equals to 0.1986 meters, or you can change it to centimeters, and say that final displacement d equals to 19.86 centimeters. So that's the max distance that it stretches. Hope you enjoyed the problem. Feel free to send any questions and comments, and have a wonderful day. Okay, thanks. Bye.